Hello, friends. Today, I want to take you on a journey into the world of spatial visualization. Spatial visualization is a cognitive ability that involves mental manipulation and transformation of visual information, particularly in 3D dimensional space. This skill plays a significant role in various fields, especially mathematics. Strong spatial visualization skills help to understand complex geometric shapes, the relationship between patterns, visualize transformations of shapes, and mentally rotate objects. These capabilities will help students to understand mathematical concepts more intuitively and solve intricate problems with greater ease. My purpose is to design a spatial demonstration program which will be useful to students in their mathematical performance. I have developed a demonstration program using videos, Python 3.1, Matplotlib, NumPy, and Pygame packages in IDLE shell. Okay, so the first shape I'm going to do is a cube. A cube is a three-dimensional shape with six identical square faces. Each face is connected to four other faces, and all the angles within the cube are right angles. The cube is like a miniature building block that can create the foundation for more geometric shapes. A cube has six faces, and each face is a square. All the faces are congruent, meaning they have the same size and shape. The edges of the cube are line segments where two faces meet, and there are 12 edges in the cube. As you can see where I'm pointing to, the blue line represents the edge of a cube. A cube has 8 corners or vertices, where 3 edges come together. These vertices are essential in defining the shape of a cube. Here is an image of a rotating cube with the vertices highlighted in red. That is where the vertice where the 3 edges are combining together. In a cube, all angles formed between the edges are right angles, meaning they measure 90 degrees, just like the corners of a sheet of paper. Cubes are commonly used in our daily lives. Think about dice or a Rubik's Cube. Understanding the spatial relationships of cubes can help you design and build objects or solve puzzles. To help you better understand how a cube can be folded into a flat shape, you can use a net. A net is a two-dimensional representation of a three-dimensional object, and for a cube, it consists of 6 squares connected along the edges. Visualizing a cube in your mind is a crucial skill, and it's a fundamental concept in geometry. This understanding can help you solve problems involving volume, surface area, and even more geometric shapes that are built upon the cube's foundation. Let's move on. The next shape we're going to do is a cuboid, also known as a rectangular prism. Here I have a cuboid right here, as you can see. So first, let's define what a cuboid is. A cuboid is a three-dimensional geometric shape with 6 rectangular faces. As you can see, I'm pointing to them, these flat planes, 12 edges over here, and 8 vertices or corners. It's essentially a stretched out box like a shape. To help you visualize it, think of a cereal box, a book, or a shoebox. Each of these objects is a cuboid. Now let's delve into the key aspects of visualizing a cuboid. A cuboid has 6 faces, and each face is a rectangle. So here are 6 of them, 1, 2, and then 4 other faces over here that I'm pointing to. These faces form the outer boundaries of the shape. Try to imagine the walls of a room or the sides of a box. Each cuboid has 12 edges. These are lines where the faces meet. Think of the edges as edges of a book, or the lines where the walls of a room meet the floor and ceiling. There are 8 vertices, or corners in a cuboid. These are the points where the edges intersect, as you can see my mouse is pointing to. Imagine the corners of a room where two walls and ceiling meet. A cuboid has three different dimensions: length, width, and height. Length is the longest dimension, width is the second longest, and height is the shortest. When you understand these dimensions, you can describe a cuboid size in a much more detailed and accurate manner. To visualize a cuboid, try to picture it in your mind. Think of a shoebox, for instance. You can see its 6 faces, imagining its edges, identifying the 8 corners or vertices. Now, imagine what happens when you stretch or squash the box. The visual spatial aspect of the cuboid changes. The core structure remains the same. Understanding the visual aspect of a cuboid is not just a mathematical exercise, it's about developing your spatial intelligence. Now the next shape we're going to do is a cone. A cone is a three-dimensional geometric shape that many of us encounter in our daily lives, such as ice cream cones or traffic cones. A cone has two critical parts: the base, which is highlighted by this red line, and the vertex, which is the green pointy dot. The base is a flat circular surface, while the vertex is a pointy tip on the top. Imagine this being an ice cream cone. The circular bottom would be the base of the cone, which holds the ice cream, and the pointy tip at the top is the vertex, which would be the bottom of the cone in this case. The side of a cone are the curved surfaces that connect the base and the vertex. These sides give the cone its distinctive shape. They are smooth and taper as you move from base to the vertex. Think about a party hat. The conical shape starts from the circular base and the sides taper up to the tip. The slant height of a cone is the distance from the vertex to any point on the edge of the base. This is crucial because it helps us understand the relationship between the height and the radius of the base. If you were to unroll a cone, the slant height would give you the length of the curved surface. The height of the cone is the perpendicular distance from the base to the apex or vertex. It helps us determine the cone's volume and various other properties. In simpler terms, it's the length from the tip of the base and measured along the line that is perpendicular to the base. As you can see, this blue line is the height. The radius of the base is the distance from the center to the circular base to any point along from the edge, which is represented by this blue dotted line. Understanding the radius is essential when calculating the surface area and volume of a cone. It's like measuring half the width of the base. Now that we've covered these fundamental aspects, let's think about why understanding the visual spatial aspect of a cone is essential. Cones are not only interesting geometric shapes, but also have real-life applications in architecture, engineering, art, and other various fields. For example, when designing traffic cones, engineers need to ensure stability and visibility. Architects may use conical shapes to create visually striking buildings or architects or other structures. Artists also incorporate cones into their works to create their unique structures and aesthetic appeals. The next shape we're going to do is a cylinder. A cylinder is a three-dimensional geometric shape that consists of two parallel circular bases connected by a curved surface. It resembles a can, a soda bottle, or even a water bottle. To describe the visual spatial aspect of a cylinder, let's break it down to several key components. The top and bottom circles of a cylinder are called bases. These bases are identical in shape and size and are always parallel to each other. When we look at a cylinder from the side, these bases appear as two perfectly round circles. The height of the cylinder is the distance between the centers of the two bases. To visualize this, imagine the distance from the top of a soda can to the bottom. The curved surface of a cylinder connects the two bases. When you imagine a piece of paper around a cylinder, we have a visual representation of a curved surface. Visualizing a cylinder in 3 dimensions can be a bit tricky. So first, we picture the cylinder as if it were a soup can. The top of the can is one base, and the bottom is the other. The side of the can can represent the curved surface, which is often smooth and cylindrical. Cylinders also come in various sizes and proportions, from slim to wide, to tall to short. This visual spatial aspect can differ depending on these characteristics. In summary, when describing the visual spatial aspect of a cylinder, we think of its two circular bases and its height and the curved surface, and how it can be cut into different cross sections. For example, if we visualize a cross section from the top, we would see a circle. Imagine objects we encounter in daily life, like cans and bottles. It will help us visualize this fascinating shape. Okay, so the next shape is a triangular prism. A triangular prism is a polyhedron, a three-dimensional shape with flat faces and straight edges and sharp corners or vertices. What sets it apart is that it has two parallel and congruent triangular bases and three rectangular or parallelogram faces connecting and corresponding sides of bases. Imagine two identical triangles placed on top of each other, like this, forming the top and bottom face of the prism. These triangular faces are parallel to each other, which means they have the same shape and size. Now picture three rectangular faces connecting the corresponding sides of the two triangles. These rectangular faces stand upright, perpendicular to the triangular bases. Understanding the spatial aspect of a triangular prism requires visualizing the third dimension. You can think of the triangular prism as a tent or a tent-like structure. The triangular bases act as the floor and the ceiling of the tent, while the rectangular faces represent the walls. To visualize this in 3 dimensions, considering how we could build a triangular prism with a piece of paper, we can start by drawing two identical triangles, then cut them out, stand them up so that the edges are parallel and the vertices will align. This will give us the basic structure of a triangular prism. Some of the characteristics are the height of the prism is the distance between the two triangular bases. So basically what my mouse is pointing to here, this is the height. The edges connecting the triangular base are lateral edges. The rectangular faces connecting the corresponding sides of the triangle are the lateral faces. The base edges are the edges of the triangular bases. Now, let's talk about a few real-world applications of the triangular prism to help us understand why the shape is important. Think about buildings with triangular roof designs, storage boxes, or even pyramids with triangular bases. All these structures can be described as variations of the triangular prism. The next shape we're going to do is a tetrahedron. A tetrahedron is one of the 5 Platonic solids, meaning it's a 3-dimensional shape with all its faces and edges of equal sides. It's made up of 4 equilateral triangles, and it's a beautiful geometric structure with a variety of application in mathematics, science, and engineering. Now let's understand the visual spatial aspects of a tetrahedron. A tetrahedron has 4 vertices that are outlined in red, as you can see here. These vertices are the endpoints of where the edges intersect. Visualize these points in space as they are the anchor points of the shapes. There are 6 edges in a tetrahedron connecting each of the vertices. The edges, as you can see, are bolded in a dark blue line. Each edge is of equal length, meaning they're congruent. Imagine these edges as the lines that form the skeleton of the tetrahedron. A tetrahedron has 4 equilateral triangular faces, and we can visualize these faces as the sides of the tetrahedron, and each face is congruent to the others, meaning they're all equal in size and shape. One way to understand the tetrahedron's spatial aspect is to recognize that it has a base. Yes, as you can see, I'm pointing it right here. This base is formed by 3 of the triangular faces and a vertex, which is the one above the base. This base provides stability while the vertex adds height. To further comprehend the spatial arrangement of a tetrahedron, we can consider the following facts. We can visualize the base as a horizontal plane with 3 points forming a triangle. The vertex is positioned above the center of the base, creating a triangular pyramid. Imagine the edges extending from the base to the vertex. These edges form the sides of the tetrahedron. To develop a stronger sense of spatial awareness, consider constructing a physical model of a tetrahedron using separate materials. In conclusion, understanding the visual spatial aspects of a tetrahedron is essential for grasping its beauty and significance in geometry. Visualizing the vertices, edges, and faces and base will allow you to appreciate the unique qualities of this geometric shape. Now the next shape we're going to do is a square pyramid. A square pyramid is a 3-dimensional shape that captures the sense of geometry in its simple and elegant form. The square pyramid is defined by several distinctive features that make it a fascinating shape. First, let's consider the base. It's a square, which means all 4 sides are equivalent, and all 4 angles are right angles. The base is the foundation upon the entire pyramid, providing stability and symmetry. Picture it as the starting point of our journey, the solid ground on which we will build our understanding. Now let's move upward from the base to the vertex. As you can see, I'm pointing right here. This single point represents the highest point of the pyramid where all 4 triangular faces meet. The vertex serves as a visual anchor for the entire structure, a pinnacle of achievement. As we venture into the spatial aspect, we'll need to think about the triangular faces. There are 4 of them in a square pyramid, and each of these triangles slope inward, merging at the vertex. These faces are slanted, not perpendicular to the base, and this slanting gives the pyramid its distinct shape. When you look at the square pyramid, you'll see the triangles leaning in, creating an intriguing visual effect. The edges of the pyramid connect the corners of the square base to the vertex. We can visualize these edges as the skeleton of the pyramid, defining its structure and forming the boundary lines that separate the triangular faces. There are 8 edges in total, each of them contributing to the square pyramid's overall alignment. Finally, the vertices, or the corners of the square base, and 1 point at the vertex, will serve as points of connections and are key to the square pyramid's symmetry. Now, why is understanding the visual spatial aspect of a square pyramid important? It's not just about geometry. It's about developing spatial reasoning and critical thinking skills. When we can visualize and manipulate shapes in our minds, we become better problem solvers. It helps us grasp concepts in architecture, engineering, and countless other fields. In conclusion, the visual spatial aspect of a square pyramid is a fundamental concept in geometry that offers insight into the world of mathematics. As we conclude this exploration of spatial visualization in maths, it is evident that our ability to mentally manipulate and understand the spatial relationships between objects plays a fundamental role in problem solving and critical thinking. Whether it's comprehending complex geometric shapes, visualizing transformations in three-dimensional space, or deciphering intricate topological structures, spatial visualization skills are essential. Moreover, they extend beyond mathematics, influencing various aspects of our daily lives, from architecture and engineering to art and design. So let's not underestimate the significance of nurturing and honing these abilities as they empower us to better navigate the multidimensional world of mathematics and embrace a broader, more enriched perspective on the challenges that lie ahead. Thank you.